Hello, my name is Samuel Schmidgall. I'm with George Mason University and the U.S. Naval Research Laboratory, and I'm presenting my work on spiking neurons as a solution to instability in plastic neural networks. So my motivating question for this work was, do plasticity rules generalize in the time domain? And we'll get into the specifics of that after some background. I'm sure, considering the conference, we all know the difference, artificial and spiking neurons. But just briefly, artificial neurons are stateless and their activity is produced via nonlinear functions. Spiking neurons accumulate information across the time domain through membrane potential, and a spike is produced when a threshold value is reached. And as a consequence of this, spiking neurons are fundamentally temporal, whereas artificial neurons are fundamentally non-temporal. They don't have necessarily a state history. Okay, so synaptic plasticity is at the heart of learning theories in the brain and is the inspirational basis for many learning algorithms in AI. These rules guide weight change based on local activity between neurons. And in previous works, these rules have been shown in application to enable adaptation during the organism lifetime or the agent lifetime or robotic lifetime. They're able to do sorts of adaptation that fixed weight networks are incapable of obtaining. And they provide a biologically inspired means of intra-lifetime learning. So shown on the top right, the equations on the top right, is the ABCD plasticity rule. And this plasticity rule is a more flexible Hebbian learning rule. This rule adds coefficients for the joint pre- and postsynaptic activity, as well as coefficients for the pre- and postsynaptic individually, along with a bias vector. Finally, the entire delta is scaled by a learning rate alpha, which determines the direction and magnitude of the computed update. And these equations are for updating the synaptic weights directly. So what the gradient descent algorithm would be doing. At the bottom is an equation for a pairwise spike timing dependent plasticity rule, where the precise timing of spikes is considered in updating the synaptic weights. Spike activity traces are accumulated at the synapse, shown by the two differential equations at the top of the bottom. And at the bottom is the plasticity rule equation, which has two parts, LTP and LTD. On the left and right, LTP is on the left, LTD is on the right. If the pre-trace X is larger then the postsynaptic neuron fires, then a larger potentiation will occur. Likewise, if the post-trace Y is larger in the presence of a presynaptic spike, then a larger depression will occur. And that's the fundamental basis of the pairwise SCDP rule. The ABCD rule provides flexible learning, coefficients on the joint activity, pre-post, and bias. And the pairwise is more precise to the spike timing, which is the benefit for that. So next, we're going to talk about evolutionary strategies. And evolutionary strategies is what is referred to as a black box optimization technique. Black box optimization means that the actual model being optimized is not considered in the optimization process, as in the actual program itself is not being observed, only the outcome. And one of the benefits of this type of optimization is that what would be in gradient descent requiring gradients, we do not need to compute those. So the non-differentiable models of the spiking neuron don't need to be optimized. The reason that spiking neurons are non-differentiable is because the gradient of the activity is zero everywhere other than during a spike, where the gradient approaches infinity. It also allows us to update both the plasticity parameters and the initial weights, which is how we learn synaptic plasticity parameters in this work. The fundamental process of an evolutionary strategies optimizer consists of creating a population of models from a single central model and using the observed outcome of this model population to update the parameters for the central model. This process is repeated for a finite number of steps until the task is solved. Updating the evolutionary optimizer requires multiple trajectories from multiple different models and uses their accumulated reward in comparison with each other to produce a central parameter update. As a product of the large number of trajectory comparisons, for computational reasons, there's an upper bound set on the length of these trajectories called the time horizon. In many settings, the finite time horizon set during training does not account for how long the model is desired to operate in practice. For example, if a robotic humanoid is trained to walk using a time horizon of 60 seconds in simulation, which it has to do, has to have a time horizon, to apply this robot in practical situations on physical hardware, it will likely need to operate for a much longer time step, perhaps on the span of 30 minutes to up to a month at a time. If we set it large enough, the time horizon doesn't affect the model's operational ability in practice, since the majority of learning models don't have any form of temporal properties and treat new environmental stimuli as completely independent from previous ones. This lack of temporality is both a strength and a weakness, since repetitive behaviors are not easily made unstable and the model remains constant through execution time. However, it completely prevents any form of intra-lifetime learning problems, adaptive learning problems, or time-dependent tasks from being solved. What we want to ask is, does intra-lifetime learning generalize to the time domain, specifically plasticity? So in this experiment, we considered a four-legged robot with the goal of locomoting away from the origin as far as possible. You can see a depiction of it in the bottom left. And we use a small hidden one-layer SNN and ANN, SNN being spiking neural network and ANN being artificial neural network, with ABCD plasticity on the synapses. Both of these networks are trained given a series of time horizons, so 250 time steps, 500 and 1000 time steps, which is about 10 seconds or 2.5 seconds, 5 seconds, and 10 seconds, as you can see. And as you can see from the graphs on the right, the red line there is the training time horizon, and everything beyond that shows the network's ability to generalize temporally. For the artificial neural networks with the ABCD plasticity, the moment the time horizon ends, the joints of the robots are observed to lock up or begin spasming as the action output begins diverging to large numbers. This causes the reward to either no longer be accumulated or to start becoming negative in the case of the first graph. For the spiking neural network on the bottom, positive rewards are seen to accumulate after the time horizon, even accumulating linearly in the case of the largest time horizon on the right, meaning there was no degradation in performance at all. A similar experiment was set up with the carpal pendulum task, where instead of observing the performance after the training time horizon, we see how long the network can continue balancing the pendulum without it falling after training. A series of policies are trained with different time horizons between 50 and 3000. In the ANN case, the relationship between the training time horizon and how long the pendulum can balance shares a linear relationship for both OJA's plasticity rule and the ABCD plasticity rule. With OJA's, the linear coefficient is 1.5 and ABCD is 15. With the SNN, however, both the SCDP rules and the OJA's rule, the pendulum was able to balance it indefinitely. We cut it off at around 1 million time steps, so it could go for around 1 million time steps. And that's after only training it for any time horizon beyond 400. So in conclusion, the purpose of synaptic plasticity is to allow learning to occur within and beyond the training time horizon period of a neural network. And hence it is necessary to consider the ability to generalize not only in the task domain, but also in the time domain. And our experiments demonstrate that spiking neurons seem to generalize better in the time domain on robotic control tasks. Thank you.